Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to be looking at some lessons learned from stability analysis and equilibrium in thermodynamics. Our goal is that we'll be able to use the criteria for stability in order to derive some useful results for a pure substance. So the basic criteria for stability is that if you have a simple single-phase isolated system that's at equilibrium, so the temperature, pressure, and that should say chemical potential are uniform throughout the system. If it's at equilibrium, then what we know so far is that ds will be 0 and the second differential of s will be negative. If that happens to be 0, then we'll need to go to the next higher differential. Similarly, we could say that du is equal to 0, or the second differential of u is going to be positive. The limit is where these are first violated, and this is going to be the limit of intrinsic stability. Now, we want to be able to mathematically analyze these, and it's actually fairly complex. So what we're going to do is let's just look at a simple algebraic expression, and we'll glean some concepts from that. So we want to know, if I look at a function of ax squared plus bxy plus cy squared, just a simple quadratic expression, what can I say to guarantee that this is going to be positive? So one way to do this is we can define some new variables. We'll just use y as y, but for z I'm going to combine the x and y variables by adding x plus alpha y for some variable alpha. So let's make this substitution. I can now go through and multiply these expressions out to get a simpler form. And if I look at this, I know that if I want this to be positive, something squared will be positive, so therefore I know that I need to require that a is going to be greater than 0 based on this. And based on this grouping, since y squared will be positive, I need to guarantee that a alpha squared minus b alpha plus c will be greater than 0. And then we have this piece here. I can't guarantee that maybe y is positive and z is negative. So therefore, the only way to guarantee that this will always be positive is to just make sure that this last piece, b minus 2a alpha, goes away, is exactly equal to 0. Based on this, I can say, therefore, that alpha will be b over 2a. If I substitute this in to the other expression, I end up with this. These two terms can be combined, and so therefore I find that c must be greater than b squared over 4a. b squared will be positive. 4 is positive. I've already said up above that a is greater than 0, so therefore this will be positive. So therefore my requirement for this to be positive is that c is greater than 0 and b squared over 4a is greater than 0. For entropy, we know that we need the second differential to be less than 0 in order to get a maximum. And so when we play the similar sort of game with those, what we find is that I need the second derivative of s with respect to u twice to be negative, and this grouping of the second differential or derivative with respect to u twice and v twice minus the mixed partials squared divided by s sub u, or the second differential of s with respect to u twice. And I need that grouping to also be negative. So let's look at these briefly, and we're going to start by reminding ourselves of the fundamental relations for s and for u. Both of those will be helpful to us. If we wish to look at s sub u, this is the same as the partial derivative with respect to u of s with respect to u, all done while holding v and n constant. So if I take the differential using the fundamental relation, I find that this is going to get me the ds du is 1 over t du, and then I'll take the derivative of that 1 over t with respect to u again. So I end up with this expression when I actually apply the derivative to the 1 over t. I get negative 1 over t squared dt. So what is dt du at constant v and n? Well, I can look at this as just being the reciprocal and now I can use the fundamental relationship for u in order to get this expression, which using the fundamental relation gives me this expression here. But v being held constant means that dv dt is going to be 0. N being held constant, dn dt will be 0. And this is just c sub v. And so we find that suu is going to be negative 1 over c sub v t squared. Now we require that this be less than or equal to 0. And if it's less than or equal to 0, well, I've got a minus here. This is going to always be uniquely positive because t squared. And so therefore what I'm requiring is that c sub v must be positive for all values of t. Next, let's look at the mixed partial derivatives. So s sub uv. This can either be written as d dv of ds du or as d du of ds dv. Since we just recently found the ds du, let's work with this one, and so I end up with d dv of 1 over t. But we know that that's negative 1 over t squared dt dv, and my variables being held constant, my path is constant u and constant n. So I need to now evaluate the dt dv. Unfortunately, u is in the path here, and so therefore I need to go to Jacobians in order to work with this. Now I've written this as a Jacobian. I did leave out the n because n is constant through all of these things. The original forms of my thetas were written as intensive variables, and so they have the n's explicitly in there. I'm working with these as extensive variables at this point in time. It really doesn't make a lot of difference. In this case, though, I've got dtu, dvu, and I want to introduce the variables t and v. So I've done that. In this first grouping, I have t's in common for both of those, so that will become my path. This is du dv at constant t. And for the second group, I have v's in common, but they're in opposite positions, so it's negative du dt at constant v. Now I also can use the n in here because, again, I was saying that it's all constant n. So in order to finish this, I need to use the fundamental relation for u. The numerator, du dv at constant t and n, I can find by taking the derivative of this differential. So I end up with t ds dv at constant t and n minus p dv dv, that's just 1, plus mu, and then the differential of n, or the derivative of n, holding n constant is 0. So I end up with this expression for the first one, and for du dt at constant v and n, we've seen that that is equal to c sub v. Next, I want to get rid of this ds dv. ds dv is one of the ones that you should recognize as being in Maxwell. And so therefore, this expression is going to be T dP dt at constant volume minus the pressure. If I substitute these in, dt dv at constant u and n is going to be, well, I've got this minus sign, I've got this subtraction here, p minus t dp dt at constant volume, all divided by c sub v. Okay, so for this next step, we want to find how S changes with respect to V twice. Okay, so that means we're going to take ds dv at constant u and n, and then take the differential of that again with respect to V. And in this case, we know that this ds dv is going to be p over t. But now I have to take the derivative of this with respect to V. So I'm going to use a product quotient rule, whatever you want to call it. And applying the product rule, I end up with 1 over t dp dv at constant u and n, and minus p over t squared dt dv at constant u and n. Now we've already evaluated dt dv at constant u and n on the previous slide. Let's look at dp dv at constant u and n. Again, noting that I've got u in the path, so therefore I want to use Jacobians. So, introducing the variables t and v, we end up with the numerator does not have any common terms, so we have to use the full definition for the Jacobian. dp dt at constant v, du dv at constant t, dp dv at constant t, and du dt at constant v. Now I happen to know this one is going to be c sub v, and it also is the same in my denominator. So that one piece I know. What about the others? Well, dp dt and dp dv at constant temperature, I can live with those. Those are going to be measurable quantities. But the du dv at constant t, I need to again use my fundamental relation. And so du dv at constant t, as we've seen before, is t dp dt at constant v minus p. Let's substitute these in. So substituting in, we end up with this expression here, and we also have an expression from the previous page for dt dv at constant u and n, and I can substitute these in to get for svv this expression here. Some terms cancel out, and the simplified form is shown in the last line. You may need to pause this to look at it and see if you agree. Stability requires that we have SUU SVV minus SUV squared over SUU less than 0. We've now got definitions for all of these second partial derivatives in terms of our TV variables, and so let's substitute those in and simplify. As you simplify this, you find that the only term that remains is 1 over t dp dv at constant t. It comes from right in here. And that has to be negative. Since t is definitely positive because of our definition of absolute temperature, this means that dp dv has to be negative, or it's a little bit more convenient to think of it as dv dp at constant temperature needs to be negative. And this we should recognize as being very similar to our term negative 1 over v dv dp at constant t, which we've defined as kappa sub t, the isothermal compressibility. And if dv dp is less than 0, then this expression here will be greater than 0. I'm going to show you one more slide. I'm just going to kind of leave it here. Frequently we write these things using Legendre transforms. It's a convenient way to go from one variable set to another. And my main reason for showing you this is that there are some generalized expressions that we can use to get similar things for looking at Helmholtz energy going to a minimum or Gibbs energy going to a minimum. And so frequently when you see other results that people have done, they have done it using this Legendre transform formalism. We will not be doing it in this course. I just wanted to make you aware. So at this point, this concludes this video, and I thank you very much for your time.